over 2 times capital S of square root of 2 over pi times y plus a constant, where capital S is, by the way, the Frenzel S integral. That should look like complete nonsense to you, all right? Which it is. Basically, Wolfram Alpha is saying you're not doing that by hand. That's the long, ugly way of saying there's no way you're doing that by hand, all right? Take more math classes, you'll figure out this is just kind of like an error function. It's a way of measuring error. So you just go dot, dot, dot. That's it. Move on to the next problem. I can't integrate sine of y squared with respect to y because it's something I've never been able to do. Oh, by the way, you could do it with a power series. You could get an approximation, but I wonder, hold on. I bet you Wolfram Alpha did it somewhere. There it is. So the program, where's the, oh, I moved it right to the place you can't see it. Here's your series expansion right here. Is your power series expansion. So if you use power series, you can get the approximation as close as you want. And that's how they're able to get a numerical answer. So we can't, we're not going to say there's no way we can do it. We can, but it'll be an approximation. What would be better? If, right, the big if this was dx dy, now that would be easier for me to integrate, because if I was integrating with respect to x, that would all be a constant, and then the antiderivative would just be that times x, wouldn't it? I wonder if I can switch it. If these were both numbers, I could, right? If these were numbers and these were numbers, I could switch it, but they're not.
Isn't that x equals sine y squared, and then you can solve for y?
Wait, hold on, say again? Isn't what?
Like the integrand, or what's in there?
Here?
Isn't that x equals sine y squared, and then you could solve for x?
No, that's z equals.
Oh, z.
Yeah, it's z equals that.
Okay.
So watch, check this out. Watch what we're about to do. This is what we know. Right? That's what the double integral tells us. Right? Those are restrictions on x and those are restrictions on y. I'm going to go backwards now and draw the region from that information. Okay? I know that my x's have to be between 0 and 1, don't they? But my y values are between what? 1 is the top and x is the bottom. So 1 being the top is this, right? X being the bottom is this. Yes or no? Y equals x, 1. And the way this integral is trying to approach the problem is by treating this region like a what? Type. They're trying to treat it like a type 1, right? I can switch the order of integration if I change it to a type 2. The question is, can you convert this to a type 2? Yes. Because if I draw my double arrow this way instead, will I still maintain the same left bound the whole time and the same right bound the whole time? Yes? That's what I'm going to do. I'm going to take the original problem. I'm going to give up on the fact that I'm never going to be able to integrate that. I'm going to go and look at the region and say, I'm going to switch it to a type 2. And then when I go back and look at this, it'll now be dx dy, if I can make the switch. So all I'm going to have to do to make the switch is, instead of looking at top and bottom, look at left and right. So this left bound, which we said was h sub 1 of y, what is that left bound on the y value? Or sorry, on the x value? 0, right? That's fixing my x at 0. It's always 0 the whole time. This one right here, h sub 2 of y, is this equation, which, what was the equation that drew this? Y is x. It's that equation solved for x instead of y, but it's already solved for x. So this is just y. Y. And then I just need to know my restriction on my y values. It goes from 0 to 1. So I can draw the same exact region, get the same exact answer, if instead of this, I go y is between 0 and 1, and x is between what this time? 0 and this side, y. Do y'all see that? That's pretty clever, right? Switch this over, double integral, 0 to 1, 0 to 1, 0 to y, and then the same integrand, switched dx dy instead of dy dx. And this one I'm not going to dot dot because I want you to actually see it happen. Any questions on how I switch this? There's a problem. There's a couple problems on your homework. I think there's 2 problems where it says switch the order of integration. So they give you this, and they want you to switch it over. And I promise you a problem like that on the final. Promise. All right, so let's do this integration. The antiderivative of sine of y squared with respect to x is x sine of y squared, right? Evaluating this, x equals 0 to x equals y, dy. Now I'm going to go and I'm going to replace x with y. So this is going to become y sine y squared. Going to replace x with 0, and we're just going to get 0. Right? So this will become, do it up here, integral 0 to 1. What did I say it was going to be? Y sine y squared dy. Now is that something you can integrate? Yes. That y out front saves you, doesn't it? It's just a basic u sub. Basic u substitution. Take this to be u. What's derivative of this? 2y. You've got it basically. So this becomes, I'm not going to go through the integration. I'm just going to expect you can do it on your own, on this side if you need to, whatever. This becomes 1/2 negative 1/2 cosine y squared. That's your antiderivative. Shall we check it real quick to make sure it is? What's the antiderivative of cosine of something? Negative sine of that something. Then times the derivative of what's inside. What's the derivative of what's inside? 2y. So what's 2y times negative 1/2? It should be y, and then there was a negative that popped with the sign. So it works. Okay, you go do it on your own. All right, and then I'm evaluating what? Y is 0 to 1. Plug in 1. You get cosine of 1, don't you? So negative 1/2 cosine of 1. And then minus cosine of 0 is 1. So minus negative 1/2. So you're going to get negative cosine, or negative 1/2 cosine 1 plus 1/2, whatever that is. And just leave it, that's the exact answer. Outstanding. If you were going to try and figure out what cosine of 1 was on your calculator, you would be in radian mode, right? If you were in degree mode, you'd get the wrong answer. It's radians unless it's specified that it's degrees. Okay, a couple of properties of double integrals. we didn't really need this. I did kind of like talk about this a little bit, but now I'll just formalize it. In that problem that we had a minute ago, where it was this one, the tetrahedron problem. Remember I asked, we want to do this type 1 or type 2? And we decided type 1 was the better approach, but that type 2 we could do it. But if we did type 2, we would have to break it into 2 pieces because the arrows this way would be different than the arrows this way, right? This right here tells you that you're allowed to do that. Split it up. So if you have some region D that you split somehow into D1 and D2, then the double integral over the entire region D is equal to the sum of the 2 integrals over each of those regions. That's not something we can just assume is true. This tells us it is. And I believe that, no, that's not the last one. So this is a major result, and it's going to be even a bigger result when we get to triple integrals. Here's what I'd like for you to try and visualize. Let's say that we have some object. I'm going to make it real simple to start off. Let's go with the rectangle. Remember when we had rectangles? Let's just say for the sake of demonstration, this was 1 and 3, and let's say this was 1 and 4. Yeah? And let's say I wanted to do some double integral of some surface over this, right? So I lay that down on the ground. I'll try and draw this a little different. Let's make this our x, our y, our z. So our rectangle would be laying on the ground like this, wouldn't it? That's our rectangle laying down. Let's say that the function on top was this function, f of x equals 1. That means that no matter what point I plug in, how high do I go up? 1. So for every point I go up 1, go up 1, go up 1. What I wind up doing is drawing this box, right? And evaluating that double integral, right? If this is 1, then evaluating that double integral gives me the volume underneath that, right? What's the volume of this box? It would be, well, how wide was it? It was 2 wide. How long was this? 3. And how tall? 1. So it's 2 times 3 times 1, which is 6. So the volume of that box is 6. Agreed? But because it was 1 unit high, isn't that also the area of this? The area of that's 6, right? So the point is this. If you're ever trying to find the area of a weird object in 2-dimensional space, you can find it by doing the double integral of the region and using 1 as f of x, y. If you do that, your answer will be the area of the region you're integrating over, always. So it's not a coincidence that the volume of this being 6 matched with the area of this being 6. They will always be the same as long as the function is 1. All right? I'll show you an example. No, I don't know. No, I don't want to do it. I don't want to do it. The reason I was going to show you that the area of a circle is pi r squared. But if I do that here, it's going to require some work. It's going to be pretty ugly. Next class, when we go to polar coordinates, I'm going to prove that the area of a circle is pi r squared, and it's going to be very simple to show. So I'd rather do it in polar coordinates than in Cartesian. So just remember that, okay? You don't want that to creep up on you somewhere where you're trying to find the area of some weird region and you forget that you can do it with a double integral. All right, this is a tough problem. We have 15 minutes. I want you, let's see, how many people have books? Yeah, is there like one book per table? I want you to look at number 28 from the book. This is on page 708. I'll tell you, I'll put all the information up here. But in 15 minutes, let's see what you can do about finding the volume of this solid, okay? It's bounded by y squared plus z squared equals 4. X equals 2y. X equals 0. Z equals 0. And it's in octant 1. There is a solid that is formed by those things. I'll give you a little hint here. All of these are planes. And this is a cylinder. See, last hint, it's a double integral. 15 minutes. I just want you working on this. You're not going to turn it in, but I want you to like actively try and get at least the picture of the ground, which I'm giving away there, but it's still not going to help you because you don't have any of the values. I'll put up a blank sheet here. Give me a second. Did I see someone raise their hand? I'll be there in just a second.
Can we do anything from this mini exam with what we covered?
Can you do anything from the mini exam? You should be able to do number 1 and number 2. I wouldn't touch 3 yet.
So we can do 2? All of it?
Yeah. Yep. Yes. Yeah, you can do 1 and 2 from the new mini exam. 2 is going to be a head scratcher, though.